So okay, so I'm going to talk about, we'll start off thinking about a case of metaphysical underdetermination with respect to different kinds of locality principles. So we're going to look at two locality principles. We've got causal locality, which is the special relativistic causality constraint, and it's the prohibition of instantaneous action at a distance. So think about things like Bell's theorem. And then we're going to contrast that with a different kind of locality principle called separability, which Einstein stated as the thesis that things claim an existence independent of one another insofar as these things lie in different parts of space. So one way of distinguishing these principles is that causal locality is temporal, it's to do with the propagation of effects over time, whereas separability is spatial and to do with the independence or mutual independence of objects or properties that lie in different parts of space. So the first principle, causal locality, comes from special relativity, an empirically well-confirmed theory, very successful theory. I think this provides good motivation for taking causal locality seriously, whereas separability also sort of conceptually formalized as supervenience. So there are different kinds of separability principles that we come across in physics. I'm looking at the conceptual metaphysical idea formalized as supervenience of the whole structure or properties of a whole structure on properties of its parts. So that ensures the independence of the parts from each other. And this is another quote from Einstein, who says that this originates in common thought. So both the metaphysical principles, both often taken, assumed in the construction of physical theories. But there are some, think sort of entanglement phenomena or the Aharonov-Bohm effect. We have these kinds of quantum motivations for rethinking these locality principles and for perhaps allowing some form of non-locality into physics. So I take whether physics should be causally local or not, or separable or not, to be a case of metaphysical indetermination. We don't know if the physical world should be causally local or separable. So metaphysical underdetermination in general, Michael Redhead offers a sort of general solution to this problem. He says that we should adopt the metaphysical principle or set of metaphysical principles that are more likely to provide fertile ground for successful future physics. So we've talked about the motivation for thinking about non-locality in physics coming from fairly well-established quantum phenomena, usually quantum. But the deciding factor about which kinds of metaphysical principles we should adopt concerns future physics. And most of the talk today I'm going to be looking at the kind of preparing a Hamiltonian system for quantization. This is looking at future physics which is not yet settled. So we've heard lots about string theory. I tend to work more on the side of loop quantum gravity. How to quantize the gravitational field is a problem that's not yet fully solved. We have these different approaches to a solution. So thinking about which metaphysics we want to use to help guide this future physics. We want to think about which metaphysics provides most fertile ground for successful future physics. So regarding locality and separability, we have a few different options. So we've got 4 logical possibilities. Rather than talk about Alice and Bob, we've adapted for an Italian audience. We've got Alessandra, who believes that physics should adhere to both causal locality and separability. This is common. People like, for example, David Wallace, in his work on the Aharonov-Bohm effect, really wants to save separability. So there are non-separable explanations of the Aharonov-Bohm effect. David Wallace criticises some of these and attempts to develop a separable, fully separable explanation, motivated by this idea that physics should be both causally local and separable. Biagio, a second guy, thinks that physics should adhere to causal locality, which is the one motivated by special relativity. But violations of separability may be acceptable in some circumstances. Claudia then believes that the 2 locality criteria can't be meaningfully distinguished from one another. In particular, when we're thinking about abstract representation of spaces. And the views of Claudia are going to be particularly relevant for what I'm going to talk about next. So we'll talk about the problem of time that comes up in constrained Hamiltonian theories. Look at a solution to that problem and how this particular solution to the problem of time exhibits a form of non-locality. Then we'll try and work out which sort of non-locality, whether it's the problematic causal non-locality, which violates special relativity.
Claudia and Dave are the same person.
Claudia and Dave are the same person. Perhaps, I mean, so I was going to say Dave.
Phases of this, the life of the setbacks.
Perhaps.
Before you said that it's not possible to distinguish. After it became more.
Okay. Okay. So, Dave's, we were not going to discuss Dave's views too much. So, thinking that physics should adhere to separability, so the different parts of space are independent from each other, but violations of causal locality are acceptable. So, perhaps this is to Morlin or Bohmians in general. Yeah, I was going to present Dave as being even more crazy than that and just sort of daydreaming, thinking about astral projection and teleportation and stuff like that. So we don't say too much about Dave, but he's just mentioned for sort of logical completeness. But perhaps you're right that his views are closer to Tim Morgan's.
Logical completeness means you're taking all possible combinations of those.
That's the idea,
right.
Yeah. So this is kind of the metaphysical problems that I'm interested in. Now we're going to look at a kind of case study. So this unfinished physical theory. I was going to draw some pictures for this, but it's not really necessary. So if we take a classical Hamiltonian theory with gauge freedom, or a time reparameterization invariant Hamiltonian theory, such as the Hamiltonian form of general relativity, and we want to quantize it. If there's gauge freedom in the classical theory, we have these 2 different options: operator constraint quantization, quantize everything, including all of the gauge observables. So the full classical phase space, we quantize all of the variables within that, including the gauge, and then eliminate the gauge freedom to get to the physical Hilbert space. What I'm going to talk about is the other option, where we eliminate gauge freedom in the classical theory. So we reduce the classical phase space to get to a reduced phase space, and then quantize everything in that. So the idea is that in the final quantum theory, Hilbert space contains only gauge invariant observables. These 2 different routes, it's hoped within the physics community that they'll be equivalent, but this isn't fully worked out yet. But where my research is within the reduced phase space quantization, where we reduce and then quantize. And I'm not going to look at the quantization part of it at all, just the phase space reduction. Okay, so we're looking at the gauge. First, we'll go through how the gauge freedom appears, and how dynamics ends up being thought of as a set of gauge transformations, which is problematic. So we end up with formal reasons for thinking that time evolution is pure gauge when we reduce the phase space, and then we have that's called the problem of time. We then have to sort of think about how to solve it. So a bit of background on Hamiltonian mechanics. So we have the Hamiltonian functional. It's a function of the QI, which are generalized coordinates, PI, the conjugate momenta, and time. This is the function from which we derive all of the dynamics. So the action is expressed in terms of the Hamiltonian, then you minimize the action and end up with a set of dynamical equations that describe the time evolution of the system. This Hamiltonian is defined on phase space, which is the cotangent bundle to configuration space being the space of the Q variables. So it's 2 n-dimensional for systems with n degrees of freedom. So n dimensions of the Q variables and another n dimensions of their conjugate momenta. So if we let chi h denote the vector field associated with the Hamiltonian, thinking sort of geometrically, what the Hamiltonian functional does is assign a vector field to the phase space, which describes how each point in phase space represents a state of the system, and then the vector field given by the Hamiltonian can be used to describe the flow of a point in phase space or its evolution in the following way, so as a solution to these differential equations. So then constraints are introduced which encode any dependence relations between the canonical variables. So the Q's are the canonical variables. So if any of those depend on one another, that can be expressed as a kinematical constraint. The constraint hypersurface is a subspace of gamma, a subspace of the phase space where all of the constraints are satisfied. So it's a set of points in gamma for which the constraints hold. So the idea is that only points on the constraint hypersurface are kinematically possible. So we have the full phase space, which represents all of the kind of conceptual possibilities, and we apply the kinematical constraints to select a subspace of gamma, which contains all of the kinematical possibilities. And this subspace has 2n minus n dimensions, where n is the number of constraints. So we lose a dimension of phase space for each constraint that we add. So this idea of applying constraints, they also kind of introduce gauge transformations. So we have adding a constraint, it selects a constraint hypersurface where all of the constraints are satisfied, but this is also foliated into gauge orbits. These were the bits that I was going to draw, but I don't know if it's going to be, this technology is really difficult, so maybe I'll just sort of describe it, and if anyone has any sort of clarification questions at this stage, then maybe ask as we go along. So the constraint hypersurface is a set of kinematic possibilities where all of the kinematic constraints are satisfied. Solving these constraints also foliates that surface into what are called gauge orbits, and points along the same gauge orbit represent empirically equivalent states. So we can't distinguish between the different states along the same gauge orbit. So in this sense, we have some gauge freedom built into any constrained Hamiltonian system. So we have some redundancy in the description. So to get a unique description of the dynamical evolution, one option would be to pick a point on each of the gauge orbit to be the true representative of the associated observable. So this would be gauge fixing. Again, this would be Tim Maudlin's preferred way of handling the situation. So we choose one point to be the true point and the others are sort of unrealized possibilities. An alternative to this would be to seek dynamics that are invariant along gauge orbits. So we look for the dynamical information which doesn't change along the gauge orbits, and that's where we find the physics.
So you're saying this is a good time for clarifications?
Yes, and
so you define these functions on phase space, and then you look at level surfaces of them. Is that one constraint surface?
One constraint surface is it. You have one constraint surface which is where all of the constraints are simultaneously satisfied.
But there will be a kind of intersection of. Isn't that how it works? Or I'm just trying to get an image of. Surely you start with an idea of a single constraint, and then you pile on the further constraints.
Yeah.
So a single constraint must be
yeah.
a level surface of a function on phase space. Is that right?
Yeah, that's right. And then the constraint hypersurface would be the intersection of all of those surfaces. Yeah.
Right.
Does that make sense?
I think so. Yeah. And so how should I picture the orbits in that?
It's just like foliating the constraint hypersurface. Yeah. You can think of it in terms of just one constraint. So you just apply one constraint. Say you've only got one constraint, then you lose one dimension from the original phase space.
Right.
So you have a 2n minus 1 dimensional constraint surface.
Right.
And the constraint itself also provides a foliation of that surface into the gauge orbit.
Yeah, that's the part I'm not sure. Anyway, I don't know what you're.
There are some details there which are kind of tricky to go through.
Right. By all means, continue.
But that's kind of the picture. So the gauge orbits, each point on the gauge orbit represents the same or empirically equivalent state. So we're looking for dynamical information which is invariant along the gauge orbit. It still only needs to be defined for the constraint surface. So this strategy, seeking invariant dynamics that's invariant along the gauge orbit, leads to a reduced phase space of 2n minus 2m dimensions. So we lose m dimensions when we restrict attention to the constraint hypersurface, and then we lose a further m dimensions from so each gauge orbit on the constraint hypersurface is mapped to a point in a new space in this reduced phase space. Is that kind of mostly clear to everyone? So
should we be honest? Or?
Yeah, please. Yeah.
It's not entirely clear to me, but I don't want to hold you up. But by all means, continue.
Okay.
I was just answering the question.
Okay. So this is the part where some pictures are helpful. So you can imagine a box which is the original phase space. We add a constraint. Just think of one constraint, that reduces the dimension by 1. So we're looking at a subspace of the phase space.
Got that.
That's divided into lines.
Right.
Points along each of those lines represent the same physical state.
Those are the orbits.
Those are the orbits,
Right.
yeah. So we want dynamics which is invariant along with the orbits. Okay, so we want the dynamics to evolve in a direction which is not parallel to the gauge orbits. That's another way to say it. Because if it's evolving parallel to the gauge orbits, then dynamics is evolving in the gauge direction, so it's unphysical.
Right.
Maybe that makes a bit more sense. So this, rather than representing the whole gauge orbit, we move to a new space where the real dynamical information is supposed to be a smaller space which contains only the real dynamical information. So rather than having the gauge orbits there representing all of the gauge freedom, we just have 1 point per gauge orbit.
The expression quotienting out arises.
Yes, yeah. That's right, yeah. Okay, so that's for any Hamiltonian system with constraints. Now we're going to think about a feature of general relativity, but we're looking at a more general feature rather than looking specifically at GR. Again, we're looking at a finite number of degrees of freedom as well. Of course, GR is a field theory, so it has infinite degrees of freedom. It's just a bit easier to work in finite dimensions. So a feature of the background independence of GR is time reparameterization invariance. So it's a way of encoding that is to introduce an extra canonical coordinate which represents the time. So time becomes a dynamical variable, time becomes one of our physical variables rather than being external to the system or being just a parameter of the trajectories through phase space. So we then have these 2 extra dimensions of phase space. We've got Qn+1, which is what was the time, and Pn+1, which is its conjugate momentum. This leads to the vanishing of the Hamiltonian by Euler's homogeneous function theorem. Again, there are lots of details that I'm missing out here. So some things like this you'll have to just take my word for, but when we introduce time as a variable like this, it changes the form of the Lagrangian, which in turn changes the form of the Hamiltonian, and it ends up vanishing. So the function from which we derive all dynamical information disappears. It's equal to 0, which gives it the status of a first-class constraint. So the constraints that we were thinking about before, that represent dependence relations between the canonical variables, they're all equal to 0. The relations between the variables are equal to 0. That's kind of the form of first-class constraints. So when we get the Hamiltonian vanishing, formally it becomes a first-class constraint. So we deal with it in the same way. We use the Hamiltonian function as a constraint to then reduce the phase space. As we've kind of gone through, and I feel like people might not be fully convinced, or maybe I haven't explained in full detail, but the first-class constraints generate gauge in the sense that they give us these gauge orbits on the constraint hypersurface. So the Hamiltonian, when it vanishes, that also provides gauge orbits. So the dynamical information and the gauge orbits coincide. So this is, you often hear that the dynamics disappears or something like this. So this is known as the problem of time. Bellot puts it quite nicely in '96. He says the problem is that the most straightforward approach to quantizing GR, recast the classical theory of the Hamiltonian system and apply the canonical rules of quantization, leads to a quantum theory which makes no mention of time. So if we were to follow this recipe exactly, the Hamiltonian is a constraint. We then quantize the observables in the reduced phase space. We end up with a quantum theory which has no dynamics, it has no dynamical evolution of the variable, which means it's not so useful for what we want from any physical theory. Is everyone kind of roughly understanding that problem before I start looking at a solution for it? Okay, so this reduced phase space where we've applied the Hamiltonian constraint, so systems where the Hamiltonian itself is a constraint, so reparameterization variant theories are also referred to as totally constrained Hamiltonian theories. That might be something that you come across. So in such theories, we've arrived at a reduced phase space where we have no dynamical evolution of the canonical variables. So this is a problem for people working on loop quantum gravity, perhaps other approaches as well. And the way that we've got Ravelli, Dietrich, and Thiemann, these three physicists and their colleagues, the way that they've tried to solve it is to take two functions on the original phase space. They call these partial observables. And they exhibit the gauge freedom, to then relate them with what they call a complete observable. So what this complete observable tells us is what the value of partial observable F is when the value of partial observable T is equal to some specified value tau. Okay, so these complete observables, they're relational. The terminology has kind of changed over time. So in the sort of 2007, around that kind of time, they were being called complete observables. Now they're referred to as relational observables. And the exact formalism has kind of evolved a bit as well. So what I'm looking at the earlier stuff, which for full general relativity turned out to be far too cumbersome, so it's changed a little bit. But the kind of conceptual ideas are the same. So these observables relate points in the original phase space, and then the reduced phase space is then we have pairs of partial observables represented by single points in this new reduced phase space. So rather than having single degrees of freedom of the original system evolving over time, we've got relations between them that are gauging variance and their representation in the new space. And then so the idea is that we can choose which of the partial observables to use as our time variable. So this is kind of the parameter invariant, and the inclusion of time as another dynamical variable. We have this freedom about what to use as a kind of clock to measure time. As long as it's monotonic along gauge orbits, we can choose which variable we want to use. So maybe to think about some intuition with this, you can have a clock. A clock just needs to be any sort of regular physical process. But the point is that whatever measures time is part of the physical system, not external to it. I don't know how I'm doing for time. Whether we need to go through an example. Okay. So maybe it helps to quickly consider an example. So if we have a pair of non-interacting harmonic oscillators, the idea is that the motion of one of these is not considered to be physical. It has gauge freedom in our representation of that. What is physical is the relation between them. Okay, so we have one complete observable represents a relation between the two oscillators. One of them being used as the clock measuring the time of the other. So Ravelli refers to the original phase space as the original configuration space that we used to derive our first phase space, the big one, before we've done any reduction process. He calls it the extended configuration space. And we're thinking about physical interpretations now. So he says that the extended configuration space does indeed have a direct physical interpretation, and it's the space of partial observables. So we're thinking about how to interpret these observables with gauge freedom. Ravelli says that when the formalism is sufficiently general, partial observables are the main quantities mechanics deals with. So they have this kind of natural interpretation as being basic physical quantities, but they have gauge freedom. So we have this reason for thinking that they're not physical. However, this interpretation is causally local and also separable. So the full phase space or the full configuration space, whether we're looking at Hamiltonian or Lagrangian transform between the two, doesn't matter so much for the interpretation, but the idea is that our representational space, when we describe the dynamics on that, so there is gauge freedom in the dynamics, but if we're thinking about observables evolving through configuration space or phase space, when it's the extended one, the big one, the ontology is completely local and separable. So it's adhering to these locality principles, but not adhering to the principle that physics should be gauge invariant. So we contrast this with Thiemann, so he's another physicist working on this same approach to quantum gravity. He says, according to Ravelli, the partial observables F and T can be measured but not predicted. We find this statement confusing because in physics, a quantity that can be measured is something observable in the very sense of the word, or the quantities F and T are gauge invariant, gauge dependent, and therefore cannot be observed, i.e. measured. We take the point of view that what can be measured and predicted are only the associated complete observables, but not the partial observables, for which a better name might be unobservables. So we've got this kind of dispute within the physics community about how to interpret these elements of the formalism. We could take it that Ravelli is motivated by locality principles. I mean, not explicitly, but at least he's adhering to these locality principles that we started off thinking about. Thiemann is more motivated by having all of the physics being gauge invariant. But what we find with these complete observables, they exhibit a form of non-locality in the sense that one sense in which they're non-local is that they can relate together states in phase space which are not contiguous to each other. I put somewhere, maybe it's on a later slide. No, it's on this slide. So there's another sense in which the complete observable picture is non-local. So if we take an infinitesimal variation in the value of one of the partial observables, specifically whichever one we're choosing to represent time, that doesn't necessarily correspond to an infinitesimal variation of the complete observable. So, if we're thinking about time as evolving continuously in the extended or unreduced phase space, that continuous motion of time there doesn't necessarily correspond to a continuous change in the complete observable. So we've got this other sense in which they're non-local. Seaman actually states that they're non-local in time. So then we're thinking about whether this is a kind of violation of special relativity, whether this is sort of self-undermining, or whether it's instead we can think of it as a form of non-separability and maybe not so problematic for the progress of physics. So is that clear to having these two different senses of non-locality that are actually exhibited by the complete observables? They're non-local in time on the reduced phase space. And they're also non-local in the sense that their relations and their relata are not independent if we take the complete observables to be fundamental. So to try and interpret this thinking about complete observables as relations between non-independent relata, we could say that one partial observable instantaneously acts on another, causing non-locality, or it could instead mean that the unreduced phase space doesn't form a supervenient basis for the reduced phase space, so we could have non-separability instead, which would be preferable. So we're thinking again in terms of these different pictures. If we want to use this kind of formalism, or a formalism that is sort of similar to this one, that resolves the problem of time in this way, it's looking like we've got some motivation for not thinking that physics should always adhere to both causal locality and separability. I haven't really given strong arguments for it, but I'm just saying it's a consequence of special relativity, and it's important for the way that we advance physical explanations to have causal locality. We're then thinking whether violations of separability might be acceptable. So on this topic, in a different context, we've got papers from Jeremy Butterfield and Ethan Gomez and Wayne Mervold, who are kind of advocates of this idea that all of physics doesn't need to be completely separable. Butterfield's written a collection of papers called Against Pointillism, talking about this idea of pointillist separability, which is the idea that all properties ultimately reduce the properties of individual points. And he gives some arguments for thinking that this is not necessarily the best way to think about physics. These are quite convincing. And then Gomez and Mervold write about the same kind of metaphysical dispute. What I've seen from them is in the context of the Aharonov-Bohm effect, where we have further motivation for thinking that some physical properties might be non-separable. In the case of things like the Aharonov-Bohm effect and quantum entanglement, we're working within the background of physical space and time, which helps us to kind of easily distinguish between these two kinds of locality principles and really thinking about what they mean. But as we've gone through and represented things in configuration space, then phase space, then different kinds of reduced phase space, it becomes more difficult to even define these properties, these locality criteria in a clear way that distinguishes them from each other. So we're sort of thinking about what this third view, what consequences that might have, how we can think more clearly about these kinds of these locality criteria when we're working with an abstract representation of space. So the fact that the complete observables are non-separable with respect to the extended phase space, which we think is has these gauge degrees of freedom anyway, maybe this is not so problematic. Because we're no longer talking about the kind of Einstein intuition of parts of space being independent. So this intuition that the parts of space need to be independent maybe doesn't correspond exactly to the idea that parts of phase space need to be independent. I'm going to skip this part because it's not fully worked out. So just some final questions for moving forward, and I'd quite like to hear people's thoughts on this. So thoughts about how we can distinguish between the two forms of locality. It doesn't seem to make sense anymore to call one temporal and one atemporal, particularly because the complete observables are non-local in time. We want to find an interpretation where this is a non-pernicious, kind of non-separable form of non-locality, which doesn't violate any special relativistic constraints. So maybe calling causal locality, separability, temporal and atemporal is not the best way to describe them anymore. Yeah, then I've really talked about that last point. The middle ones, I think maybe it's time to stop soon, right? Yeah, so I'll kind of wrap up there. There is this link when we're thinking about separability. It kind of links to the idea of intrinsic and extrinsic properties, and properties being defined at points or holistic properties. That's kind of approaching another metaphysical debate, which is quite a big kind of word. So I'll leave there. I'll leave it there and see if there are any questions. Thank you.
Thanks, Lucy. Thanks, Lucy. Very interesting talk. So as usual, raise your hand. Question, finger for follow-up, and same rules of engagement as before for people who are online. So you can write Q in the chat if you have a question, and F if you have a follow-up. Alexander, you go first.
This is really a question. Just while you're answering questions, could you put up your double pendulum screen so that I can read it out loud?
It was not a question. Now you have to ask a question.
Well, I'll read it and you can, while I read it.
Okay. I think someone in the chat has a question.
Yeah, Pedro.
Huh? Pedro. Okay, Pedro, please.
Thanks, Enrique, and thanks, Lucy, for this interesting talk. Okay, I just have a very general remark. I mean, the thing is that these complete observables and partials that Rovelli, Tiemann, and colleagues are putting forward. I mean, one should keep in mind that basically the variable that is taken as a clock itself is subject to dynamics. So the problem is that there is no guarantee in general that this clock variable, so this degree of freedom, is going to function as a clock in every regime. So its own dynamics means that it's no longer monotonic. So this is, of course, something that has been realized for many years in basically this relational approach to quantum gravity, the quantum gravity spin forms. And there are people, of course, trying to tackle the issue by, and I think this is one of the motivations why Rovelli thinks that basically this sort of fragmentary view of reality, this constellation that basically he champions in his relational approach to quantum mechanics. So this is just to remark, because there is basically in line with your final comments in the next to last slide, if I recall well. I think Gomez, you mean Enrique Gomez? Okay, one of the things that there is this proposal that goes back to Julian Barb about Machian ideas, and precisely their goal is to basically extract one basically clock, a variable that should function as a clock under all circumstances. So in this case, it basically is definitely a holistic component in the sense, okay, it's causally local, but there is, perhaps one should be careful in basically the definitions, but okay, there is certainly a holistic component in this approach, and this is basically by what you mean by basically breaking this separability condition. So, and thereby you get a notion of time that emerges, but it's basically the same for all observers. So there is this grasshopper effect, which is a fancy name that basically has coined the literature for this issue. So, okay, well, just wanted to point out that general comment. So, thanks.
Yeah, interesting. What do you mean by the grasshopper effect? Did I hear that correctly?
Yeah, no, this is just actually I don't know was the first one who coined. It's just basically what it means is this basically that the failure of monotonicity of the degree of freedom that is used as a clock variable. So you basically this jumps between what you say basically that the time runs backwards, because at some point its own dynamics make the degree of freedom basically behave in an awkward way. So basically hence grasshopper effect. So but never mind the name. So it's just that so, and this is what takes us, some of us, because I favor this approach by Barbour and colleagues, so to this basically Machian approach to dynamics, which it's definitely ontological and sort of holistic component to basically dynamics, and in particular to the issue of time. So just basically as an alternative to basically the proposal that you've been given in your talk. So just a general remarks.
Yeah, interesting. Thank you.
Yeah, thanks.
And I agree with you from the sort of purely metaphysical perspective and looking for the kinds of metaphysics that's going to be useful for physics. I agree with you that including utilitarian components it seems helpful and not something that we should be ruling out. This is just a kind of example of using this kind of non-separable metaphysics, but there are, yeah, of course, other ways of implementing similar metaphysical ideas or changes in our previous background. Thank you.
Okay, thanks.
Questions? No. Then well, I think we have time, yes, for one last question. Since we're a bit late, we need to move to the next speaker, but I wanted maybe to ask you to tell a bit more about this connection with the analogy, let's say, with electromagnetism. Where do you think it takes us? Because so what I'm not entirely clear on is what would be the equivalent of this relation observables in electromagnetism, some kind of Wilson line, right?
So either the Wilson loops, or if we're thinking about a Helmholtz effect, would be the Helmholtz.
Okay.
So they're non-separable in the sense of not being defined at individual points in space. Or the alternative kind of account of the AB effect that I've been looking at, David Wallace's work,
yeah.
Which he tries to make separable, but then he ends up taking to be basic the covariant derivative of the phase, and it's sort of formally separable, but then it looks like the covariant derivative of the phase is describing, in a sense, non-local properties, or at least extrinsic properties.
But so the analogy with this generativistic case would be something like that. The equivalent. So what I'm not getting basically is where would the Wilson loop live in the gravitational case? Would be so the equivalent of the Wilson loop in the gravitational case would be a space-time loop. Would be a space-time in phase space. Looks like more loop in phase space.
So maybe the analogy is not quite as tight as you're
Okay.
expecting it to be. So it's only that we have non-separable variables. So
Okay.
so in the AB effect, or like a Wilson loop is defined. It is a quantity defined on a whole loop, not a point. A complete observable is a quantity defined relating point.
Okay.
So it maybe relates more closely to the covariant derivative of phase, which is like a vectorial quantity.
Okay. So
we're describing a relationship between points.
so the idea would be that something like a gravitationally dressed observable would not necessarily count as a complete observable, right?
So that kind of
Gravitationally dressed observable. So, for example, you take some gravitational degree of freedom, you propagate to the boundary, you come back as you do in a Wilson loop, right? And you measure it. That quantity should be gauge invariant. This is the case with the Wilson loops, right? So it would be analogous to this, a complete observable or not?
Yes.
Oh, okay. So yes, then maybe it is as analogous.
I believe so.
If something like this is counts as a complete observable, then they seem to be quite similar.
Yeah. In some cases, but the point is the idea of complete observable is
It's
more
more
general.
general.
Than this.
I see.
Yeah.
I see.
So yeah, that would be an example of a complete
Okay.
observable.
I see.